Right, hello, and welcome to the Math3711 and 5706 seminar. We'll be going through the content of algebra today. I'm Ronald, and then we'll be led with Dale, Kieran, and Martin. And so we're going to end up with introducing rings to you. And my job here is to first get you through group theory and the basics of homomorphisms. So, I think it would be pretty good to start with some examples of groups. And some examples that we have are, for example, the integers with addition, right? So we can add 0 and 1, we'll get 1, 1 and 2, we'll get 3, right? We also have things like rotations with a mapping of composition. And maybe we have something like invertible matrices and we can multiply them together. And the thing with this is they seem like really different structures, but what algebra is about is we can essentially create a class that will identify properties about all of them. And so if we prove something about the class, then we can prove something about every single group. So what might some properties be? Well, first, we know that they are a set of objects, and generally we denote the set as G. Now, we also have a binary operation, right? So in our first example, we had an operation plus, and we had a set Z, right? And this operation is binary, which means it takes in two elements of G and then spits out a new one. So for example, in addition, maybe we have 0 and 1 as our inputs, and then that outputs a 1 when we add them together. Now, we also have something like associativity, so it doesn't actually matter what order we do the operation in, right? So we can do GH first, then K, or HK first, then G, and you might see this in something like addition, where we have A plus B plus C, and it doesn't really matter where we put the brackets. We can put them here or here, but in the end, the output is the same. The next thing is we have an identity element. So in this case, we have an element which we would usually call 1, and 1 multiplied by any single element is just that element by itself. Right, so you might remember 0 plus A is equal to A, right? So no matter what element you add 0 to, that will remain A. And finally, we have something like inverses. So every element in G has an inverse element H, where if we multiply G and H together, we just get our identity, right? So we can multiply GH to get 1 and HG to get 1. And keep in mind that this is not necessarily commutative, so we're never really guaranteed that this is equal to HG. So when is it actually equal to HG? Well, we say that if it is for any two elements, H and G, then we can say that the group is abelian or commutative, because we can commute any two elements, right? So an example of that might be our integers with addition. Obviously, A plus B is equal to B plus A, but in something like multiplying matrices, the order actually matters. So A times B and B times A are not equal to each other, right? So we have integers with addition being an abelian group, but matrices with matrix multiplication being not an abelian group. Right, so let's get into our first question. Right, so our first question pretty much says, hey, we have group G, so maybe G already had a operation, let's call that operation star, right? And we have an element U in G. We can define a new multiplication where A circle B is equal to A inverse U B for all A and B and G, right? So the first thing is we have a set G, right? Obviously G is a set, but then we also need to show that we have a binary operation which follows our rules such that we can input 2 elements in G and output 1 element in G. Obviously A and B are 2 elements in G. We just need to make sure that this is an output in G. Well, originally G is a group, and this is actually using the original group multiplication. So by definition, we know that A, U inverse, and B, that is going to be an element of G because the original operation has its output in G. So that's essentially our first condition for a group. The next thing is it has to be associative, right? So for associativity, what we can do is we can say, hey, we'll have A, circle B, and circle C. We'll evaluate A circle B first to get AU inverse B, circle C. Evaluate that to get this. We notice that we can actually just put brackets around here as well. And so we can turn this part back into a B circle C and this part into an A circle B circle C. So no matter which way we evaluate this, we see that it's going to be equal, and so we can say that it's associative. The order of evaluation does not matter. That's our second property that groups have. The next is that we have an element U, right? So U is our identity in this case, and the reason is because U dot G is going to be equal to G, and G dot U is going to be equal to G. And so where did we actually come up with our element from? Well, the way you might be able to think about it is we want A circle B to be equal to maybe A, right? If we want B to be our identity, and we know that A is equal to A U inverse B. So if we have A U inverse B, we know that U inverse B has to be the identity element, and so B has to cancel out with this U inverse, so B has to be a U, right? So that kind of gives us the clue that we want our identity element to be U, and we can check it like this. The next thing is we want to know whether inverses exist, and so we can kind of come up with inverses in a similar way. We want the inverse, so A circle B, to be equal to our identity, right? So by definition, our identity is this one here. In our original multiplication, we had our identity as maybe 1, for example, 1G. But in this new group, our identity we just found was U. So we want to find out when is AOB equal to U, and we let this be A U inverse B, and we can rearrange this to essentially get B is equal to U A inverse U, right? So this is essentially our inverse, and we can verify this by having G dot U inverse G U, and we see that that's equal to U. Then we do it on the other side, show that that's equal to U, and so overall, we know that any element G has an inverse, particularly U, G inverse U, for our new multiplication, and so because it has all of the rules that a group has to follow, associativity having an identity element and having all the inverses, we can say that this overall forms a group. So now we have something like a subgroup. The group has a lot of criteria, and so an easier way of proving something is a group is if we have something we already know to be a group and a subset H, we can say that H is a group as well, but it's contained entirely in G if we can say that it follows all the rules of a normal group, right? So, for example, it has to have an identity element. It has to be able to follow the operation, right? So we want our star to go from H times H, which means it inputs two H elements and then outputs a H element. And to confirm this, we can check closure on a multiplication, which just means if we have any two elements in H, then we can multiply them and check that if it's in H. Then we also have closure under inverses. So if we have an element in H, then the inverse also exists in H. And by having all of these, we know that this is a group. We don't actually have to check for associativity because associativity has to do with the actual operation, and because it shares the same operation with something we already know to be a group, we know that this operation is still associative. And if we know that H is going to be a subgroup of G, we can write it as H less than or equal to G. And so this means that it's a subgroup. Now, let's look at permutations. Permutations are essentially just a way of taking some set and rearranging them, right? So for this rearrangement, what we can do is we can essentially look at some kind of bijection, right? We can have a sigma where we're taking a bunch of elements and maybe changing their order, right? If it's a bijection, that means every single element here has to be mapped to a different element here, and they have to be a one-to-one correspondence, which means that this will essentially just take all the elements on the left-hand side and then rearrange them into the new order on the right-hand side. And so the set of every single bijection of this form is going to be a permutation of S because it permutes the elements. And if our set is the numbers 1 to n, then we can say that perm S is denoted by Sn. So we have two ways to actually denote this. We can have something like this, where essentially we're saying, hey, the first element 1 is mapped to its new spot 3, the second element is mapped to its new spot 5, the third element is mapped to its new spot 1, 4 stays in the same place, and 5 is mapped to its new spot 2. Or you can represent them as cycles, so maybe we have a swap between 1 and 3, then a swap between 2 and 5, and hopefully you see that these two forms our equivalent. Next, we have a generator subgroup, and a generator subgroup essentially just takes some set and then makes the smallest group possible that contains every single element in it. So how does it do that? Well, to be a subgroup, you first have to contain the identity. So we actually have this, which says, hey, the identity is going to be in our subgroup. The next thing is we need to make sure that every single element is in there when we multiply them together, right? We have to be have it be closed under multiplication. So any elements in our subgroup has to be in the form of a multiplication of elements in S, right? So if we have, for example, something like elements A, B, C, DE in our S, then we need to make sure that AB, AA, AC, DE, every single possible multiplication that can exist to also exist in the subgroup. And that makes sure that it's closed under multiplication. Then the next thing is we also need to make sure that we have inverses, right? So what we do is we have our sets A, B, C, D, E, and so what we do is we take all the inverses and then we kind of do the same thing. We can also have multiplications of their inverses, right? So that means that any element that we create down here, right? So AB, we can have its inverse, which is multiplication B inverse times A inverse, right? And that allows us to make sure that every single inverse is in there, every single possible multiplication is in there, and the identity is in there. So overall, this is a subgroup. And so we say that this subgroup is generated by S, since every single element is a multiplication of things in S or S inverse. Now, if we have a group and we know that it's generated by a set S, which is finite, then we can say that that group is finitely generated. And if a group has a set with one element, maybe that element is A, we say that it's cyclic because it either forms a cycle or it has an infinite number of elements, and we know that every element has to be some power of A, where n is an integer. Now, we can look at cosets. If H is a subgroup of G, then we can say that GH is a coset where it's a set of every single element in the form of G times some element in H for some G and G, right? So this is the coset GH, and we can have the set of cosets be denoted by G on H. And the reason we specify left coset is because we have right cosets as well, so it's the same concept except it's multiplied on the right. And obviously, if we have the group being commutative, then we know that the left coset is equal to the right coset. And what this allows us to do is it allows us to use something called Lagrange theorem, which pretty much just says the size of G is equal to the size of H times the amount of cosets there are of G on H, right? And this is important because this essentially allows us to say that any subgroup size is divides size of G, right? We have H, his size, right, dividing the size of G. So this is pretty important because if we're ever trying to find maybe subgroups, right, and maybe we know that we have G being equal to 9, then we know that the factors of G have to be every single possibility that H can be. So H can have a size of 1, 3, and 9. 9 and 1 are trivial, and so the only thing that we have to look for are subgroups of size 3. The next thing we want to know is a normal subgroup. So if n is a subgroup, then we can say that it's a normal subgroup if the left cosets are equal to the right cosets for every single G, or if G and G inverse is an element of n, where n is an element of n for all G. And the reason we need this is because it essentially allows us to make our set of cosets into a group. So if n is normal, then we can say that G on n forms a group with all elements being in the form of some element g times n, and we can define multiplication as g dash n. And you might be able to see this as being like, hey, this can actually kind of be swapped. So we have g dash n in this case, and then we just have n times n. We know that a set multiplied by itself is just itself. So overall, we have the multiplication gn times g dash n being equal to g dash n. We also have an identity element, which is just n, and an inverse where the inverse of gn is g inverse n. So now we're moving on to group homomorphisms, right? We have groups, but maybe we now want to have a mapping from one group to another. And so we can call it a homomorphism if we have our domain and codomain as groups, and for any two elements g and g dash, we can essentially split them up by the phi. Right? And we have a bunch of different types of homomorphisms. We have a monomorphism, which just means that it's injective, an epimorphism, which is surjective, an isomorphism, which is bijective, and an automorphism, which is an isomorphism from G to itself. And isomorphisms are pretty important. And the reason is because while we have two groups, which might have maybe the same number of elements and act similar, we might not be able to say that they're the same. And so an isomorphism pretty much just says, hey, these groups essentially act in the same way, and so we can say that they're equivalent by some sort of measure, right? Because in a homomorphism, this essentially allows elements to still act like a group. And so if we find a bijective function from G to H, then we can say that G and H are isomorphic, and so G and H are essentially equivalent. Next, we have the kernel. The kernel is pretty much the same as, I don't know, maybe like finding the root to a function, right? We just want to know what are the elements in G such that they get sent to our identity 1. And we know that the kernel is a normal subgroup. The next thing is we have the image, right? That's pretty much if we put every single element from G through our function, what would the set of outputs look like, right? Every single output that's possible is in our image. And whoops, this is meant to say image. The image is a subgroup of H. And essentially what this allows us to do is it allows us to form a isomorphism theorem. If we have some phi, which we know to be a homomorphism from G to H, then we can find that G over the kernel phi is isomorphic to the image of phi. And we know that this is possible because the image of phi is a subgroup and the kernel is a normal subgroup. So G on the kernel will form a group based on the quotient. Right? This is pretty important because this allows us to find isomorphisms maybe a bit more easily. Rather than finding a bijection, we might be able to find just some homomorphism with a given kernel and an image, right? Because they might be like, hey, we have something in the form of, we have something in the form of G on K equal to some H, right? We can just make, somehow find a function K as our kernel and H as our image, and that allows us to use our first isomorphism theorem to show that this is true. And the next thing is, if we have H and N, which are normal subgroups of G, and N being a subgroup of H, we can essentially cancel the denominators in this fraction, and we get G on N over H on N being equivalent to G on H. In our third isomorphism theorem, if we have H being a subgroup of G and N being a normal subgroup, then we can conclude that Hn is a subgroup of G and H intersection N is a normal subgroup of H. We have this isomorphism, Hn on N being isomorphic to H on N intersection N. Now, here's a question from 2021's final exam. We have HA, which is a collection of subgroups in G, and all of them contain K, and we know that K is a normal subgroup. We want to show that the intersection of every single HA on K is equivalent to the intersection of all the HAs over K. Well, how do we do that? This form is kind of similar to what we might have seen before. It's essentially just some group, right? We know that the intersection of a bunch of groups is a group itself. So we have a group over something which is isomorphic to something else. So that kind of suggests to us, hey, maybe we can make something where K is the kernel and we have this as our image. And turns out we actually do have a natural homomorphism, right? We have a homomorphism from our group here to our group here, right? And the homomorphism is simply we have an element G and that gets mapped to G times K, right? So on our left-hand side, we have a intersection of a bunch of subgroups. So it's just going to be a bunch of elements in our overall group G. Then our output is going to be the intersection of a bunch of things in the form of GK, right? Because obviously we have the intersection of everything in the form HA on K, and we know that this is going to be the set of cosets where we have G being an element of HA multiplied by K. We know that G is an element of HA, but then we also know that GK is an element of every single thing in the form of HA on K. So we realize that this element right here, our G, because it has to be a part of HA for every single HA that exists, we know that this is also an element of the intersection of all the HAs. So hopefully you get to see why this can actually work as a function. The next thing you might notice is, hey, we need to prove that this is a homomorphism. Hopefully that's pretty clear to you. Pretty much you just have phi of G, G dash being equal to G, G dash K, and that's equal to GK times G dash K, which is just phi of G dash, right? So obviously it's a homomorphism. And finally, we just need to know, hey, what is the kernel of this? Well, we want GK to be equal to K, and this is only true if G is an element of K. So we know that the kernel of phi is just K, and we want to know the image. Well, what we can see is that any element in the form GK, since we know that G has to be in our intersection, actually has a mapping, right? GK is just simply equal to phi of G. So it turns out every single element on the right-hand side has a mapping from the left-hand side. And so we can say that it's surjective. Well, if it's surjective, then the image is actually just equal to this right-hand side. And so from our first isomorphism theorem, we see that this group right here over our kernel K is isomorphic to our image. And that gets us our isomorphism up here. All right, I'll be passing it over to Dale, who will give you a rundown on direct products and sums.
All right, so today we're going to look over direct products and sums. Okay, so external direct product. Firstly, what is an external direct product? So that is essentially the group formed by the Cartesian product of multiple groups. So given all of these groups, G1 up to Gn, then we call the Cartesian product of these groups, so G1 times G2 times and so on up to Gn. This is called the external direct product. And the group operation here is just component-wise multiplication. So for example, here's an example. If I take the group of positive integers under multiplication, then G times G, this is, so remember this is G H, where G and H are both in R plus. I guess they're both in G. If I multiply two of these together, then I just multiply the first component together and then the second component together. So in this case, if I take 2, 3, and 4, 5, my first component here comes from 2 times 4, and the 15 comes from 3 times 5. Okay, so here's some things we can do with them. There's these things called a canonical projection and a canonical injection. What the projection essentially does is it takes an ordered n-tuple of terms, and then pi k, which means the projection onto the essentially the kth entry, it will map to the kth group, and it'll just spit out the kth entry in the tuple. Right, so you can think of it as projecting the product of a group onto just that one group. So this is an epimorphism that should be fairly easy to prove. For example, if I have 1, 1, and so on up to, and then the kth element is gk, and then everything else is 1, then this would get mapped to gk for every k you choose. And then for the canonical injection, so this takes some element, it does essentially the reverse. I take one group and then I map it to the direct product, external direct product. So I take, for example, gk, and then I inject that into the kth component. Okay, it's named the injection because it is injective, which also should be fairly easy to show. Okay, so here's an example. Let's take the canonical projection of from this product of groups to just R star. So since this is pi 2, this means we're projecting the second group. So it means we're extracting out the second element, which means if I take pi 2 of this, these 4 numbers, then I'm just extracting out the second one, and it should be 3. And for example, the canonical injection of R star into this product. So since it's I3, that means that whatever input we have gets mapped to the third element. Okay, and everything else is set to the identity. So right now this would be, so something, something, this should be minus 5, and then something. And these should all be the identities. So R under multiplication, the identity of that is 1. R, the identity for that is 0, because that's under addition. And then S4, well, the identity for that would be, I guess you denote it like this. Right, it's the identity permutation. Okay, so what's an internal direct product then? So we've talked about external ones, what's an internal one? For a product to be internal, we need some conditions to hold first. So first, let's say that all of the groups that we're interested in are a subgroup of a bigger group G. And we need 2 conditions. The first condition is that elements between the groups commute. So for example, if I had G1 and G2, if I took G1 from G1 and G2 from G2, then these should commute. But that doesn't necessarily mean that each group is abelian. So I couldn't say this. So this would not necessarily be true. And then the second condition, if you've done vector spaces, then this should be kind of the group analog of linear independence, or of independence, I should say. So GI is independent from all the other groups, in that if I take all the elements that I can generate using all the other groups, then the only element in common with GI is the trivial element, right? It's just the identity. Okay, under these 2 conditions, we get something called the internal direct product, which is just this. So it's the set of elements that look like G1, G2, and so on up to Gn. And under these conditions, this is isomorphic to the external direct product. So we can define this map here from the external direct product to the internal direct product, where we map the tuple, the n tuple, to just each term multiplied with the next. Okay, and that turns out to be a bijection. Okay, so some nice thing that happens is that if we take G times H and take the quotient group of that over 1 times H, that's actually just isomorphic to G. And yeah, so this is nice because it just follows our intuition of like cancelling the H's, even though that's not like technically the right way to think. It does work in this case. But it is not necessarily true kind of the other way around, where if I take the quotient group and then I multiply it by, let's call it the denominator, H, the isomorphic to the original. So I can show you why that's not true, just with a quick example. So when things are isomorphic, a few things happen. If you have an element, then it preserves the order of that element under the isomorphism. You could preserve subgroups. You could also preserve isomorphisms, also preserve normal subgroups. And there's probably other things that I'm forgetting here, but the main one that's important here is preserving order, okay, of an element. So for example, let's take one of the quotient groups that we're familiar with, Z mod MZ. take the product of that with mz, and we want to see if it's isomorphic or not to z. Okay, so in terms of preserving order, notice that z mod mz, so one example of, one element of this is 1 plus mz, and for the sake of simplicity, let's just make the other one the identity. So that would be just mz. Okay, so what's the order of this? So how many times do I need to add 1 plus mz to get back to mz? Well, that would be m times. And since this mz is always the identity anyway, then we don't need to worry about that. So this has order m, which is finite, provided that m is a positive integer. I guess we can stipulate that. But if I look into z, this doesn't have any element of order m. So since isomorphisms preserve order, that means that these are actually not isomorphic. Okay, now let's talk about direct sums. So the only difference between direct sums and direct products really is the fact that now we're talking about abelian groups. So remember how in abelian groups we prefer to say addition instead of multiplication. And so the internal direct product for abelian groups, it's called the direct sum. So let's let a bunch of groups be a subgroup of the abelian group G, so a similar setup to before. And let's say that these subgroups generate G. Then this larger group G is the direct sum of each of the subgroups. So this is how it's denoted. If and only if, we can think of this as independence. Right, so remember with, I guess this looks very similar to linear independence for vector spaces. If I have a bunch of elements added together, one from each group, then the only way that the sum can equal to 0 if they are all equal to 0. So let's say that A and B are abelian groups such that the direct sum is equal to G. Let's prove that if these two have finite orders, then the order of A plus B is the LCM of the order of A and the order of B. Okay, so with the direct sum, due to this notation, we already know that if I have, let's say, A plus B equal to 0, then I need A to be 0 and B to be 0. Right, that was just from this condition here. And we also know that, I guess, they're disjoint, which really is just saying this. So how do we go about proving this? Well, let's write some numbers for the order of A and B. So I'm going to let order of A be m, and let order of B be equal to n. And then I'm going to consider k of A plus B being equal to 0. And I'm going to try to find a condition on k. And if I find the smallest k for which I can make this work, then that would be the order. Smallest positive k. Okay, so if k of A plus B is 0, then that means ka plus kb is equal to 0. But this is an element of A, kb is an element of B, and due to that condition from before, that means that ka is equal to 0 and kb is equal to 0. Okay, but if A has order m, then that means that k has to be a multiple of m, so m divides k. And similarly here, since B has order n, then n has to divide k. So k has to be an element that is divisible by both m and n, and the smallest such element is the LCM of m and n, which is the LCM of the order of A and the order of B. Okay, so this is how you would prove that. Okay, for another example, consider the group G generated by these three elements with all of these conditions holding. Prove that G is isomorphic to Z times Z mod 3. And I don't want to find an isomorphism between them. I want to do this just by using some things we know about groups. Okay. So what would we do here? Well, let's look at each of the conditions and see what they mean. Let's take this, for example, equaling to 1. If I multiply the right by y, and then the right by x, well, what I would end up with is xy equals to yx. So this tells me that x and y commute. If I do the same thing with this term, so multiply the right side by zx, then I find out that xz is zx. And for this last term, I find out that yz is zy. So what I've found from here is that G is abelian, right? Because each of the three generating elements commute. What's the consequence of that? So since every element in G is a word in x, y, and z, then since it's abelian, I can move all the x's to the left. I'll move all the y's to the left. Let's say the total power is m. Then I can move all the x's to the middle, and then all the z's to the right. Okay, where k, m, and n are integers. Okay, so what else do we know? We know that x to the 5z is equal to 1. Okay, so that means that z is equal to x to the minus 5. This means every z we have can be replaced with x. And the consequence of that is we can merge this into just x to some other power. I'm going to call it n dash. So right now, any element in G can be written as y to some power. I'll rename them. It's just y to the m times x to the n for some m and n that are integers. Okay, and now what else do we need? We know kind of two things from here. Actually, I'm not sure if this is too clear, but y cubed equaling 1, what they intend to say is that this means that y has order 3. What they also intend to say is that x and y are independent. I guess I should say the actual groups generated by x and y, they have an intersection of 0, of just the trivial set, as trivial intersection. Okay, so what does that mean? Well, since now I'm essentially generated by y and x, okay, y has order 3, x has order, well, we actually, it doesn't say anything about x to the some power equaling 1, so we can say that as order infinity. And that means since G is now the direct product of the group generated by x and the group generated by y, I should say that it's the group G is equal to the group generated by x times the group generated by y, which we know is isomorphic since these are independent. and that they commute to group generated by X times the group generated by Y, like this. And since the group generated by X, it's an abelian group of order infinity, so it's isomorphic to Z. And for Y, it's a abelian group of order 3, so it's isomorphic to Z mod 3. And that's a rough sketch for how you would prove this question. So yeah, this is the solution they gave. So just to recap, we found from the first set of equations that X, Y, and Z commute, so that every term looks like this. X to the 5 Z equals 1 implies that any Z can be reduced to a power of X, which means I can essentially remove dz, and every term can be written like this. This should be an intersection. So the intersection between the groups generated by X and Y is 1. And since there's nothing relating X and Y, apart from commuting, then that means G can be written as the direct product of X and Y. Okay, but since Y has order 3 and X has infinite order, then I get the product of these two groups. Okay, now let's talk about finite abelian groups. It turns out that every finite abelian group can be reduced to a direct sum of cyclic groups. Yeah, so this proof takes a while to prove, but we'll first discuss how to classify cyclic groups. So it turns out that the only cyclic groups that exist up to isomorphism are Z and Z mod M. So Z mod M, these are cyclic groups of order M. And Z has order infinity. Now you can think of Z as Z mod 0. So it's also valid to say that all cyclic groups are isomorphic to Z mod M, where M is not just a positive integer, but an integer greater than or equal to 0. For instance, if we take the group of the nth roots of unity in complex, since this is the cyclic group, you should know that this is generated by, let's say, omega naught. Where omega naught is the solution with the least argument. Since mu1 is equal to this, and this has an order of n, then it's going to be isomorphic to Z mod n. And then if we look at the group of the powers of 2, since elements have infinite order, because you can't take one of these elements to some power and have that equal to 1, then it's isomorphic to Z, right? Because it's infinitely, each term has infinite order. Okay, so here's some theorems about this. So to find, I guess to find a product of cyclic groups that an abelian group can be decomposed into. Okay, so firstly, this is actually true. If I take any finitely generated abelian group, G, then I can decompose it into, okay, this is actually slightly wrong. In here, there should be, oh, sorry about that. There should be Z to the S times, and then the rest of this. So G would be isomorphic to Z to the S times Z mod something, Z mod, okay, I'll just rewrite this. So G is isomorphic to Z to the S times Z mod H1Z times Z mod H2Z, and so on, up to Z mod HRZ. And the things we need for this to be true are that, so R and S are natural numbers, and that each of these numbers, they're in sequence and divide each other. So h1 divides h2, which divides h3, and so on. Okay, and so if you want to find every subgroup of a finitely generated abelian group, or let's say every subgroup of some order, which we will do next, you can use this theorem to find all of them. And then there's the Chinese remainder theorem. This is kind of saying that if I have... Okay, so firstly, where does the Chinese remainder theorem come from? It comes from the set of equations. Let's say they tell you that n is equal to, or is congruent to k1 mod p1, k2 mod p2, and so on, up to, let's say, kr mod pr, where each p is coprime. Then there's a unique solution for n mod the product of all the p's. So this is like a group theory analog of that. If n1, n2, and so on up to nr are all relatively prime, and that their product is n, then what I can say is that z mod nz is isomorphic to kind of the product of each modulo. That sounds wrong, but hopefully you get the right idea from that. Okay, now let's tackle this question. How might we use these to find all the finite abelian groups of order 360 up to isomorphism? So remember, every finite abelian group can be decomposed into this. Well, I guess I should circle my one. Into this form. Okay, so our job now is to find. Firstly, since it's order 360, we can ignore the z to the s. And then we just need to find some numbers, h1, h2, h3, and up to hr, that multiply to 360. And such that h1 divides h2, divides h3, and so on. Okay, so to do that, let's find the prime factorization of 360, just to make this divisibility easier to work with. So this should be equal to 2 to the 4 times 3 squared times 5, I believe. Um, 16. Let me just check if this is correct. That is not correct. It is 2 cubed. Okay, then one possible group, for example, would be z mod 360z, just because there's only one thing here, so of course this part holds, and they all multiply to 360. Another one we could have is, for example, let's say we start off with z mod 2z, then we need to like kind of chain it up. So I need to find something that is a multiple of 2. And for example, I could use just whatever's remaining, z mod 180z. I could do that with the 3 as well. If I take z mod 3z, I could times that with z mod 120z, because 120 is a multiple of 3, and these multiply to 360. But what, for example, doesn't work, what wouldn't work is if I wanted to use z mod 5z, because there's no other factor of 360 that contains a factor of 5, because we've already used up all the 5s in the prime factorization. Okay, so what more could we do? Well, we could take, for example, z mod 6z, so you can think this of 2 times 3. Then I need to grab another 2 and another 3 in my next term. So if I take everything else, then that actually will also work. And you can keep doing this process until you list through all of them. And you'll find that these are all the possible groups, finitely generated abelian groups. Oh, sorry, just finite abelian groups that have an order of 360 up to isomorphism. Okay, and that is the end of this segment. I'm now going to hand over to Yiren to talk about group actions.
Okay, hi. I have realized my mic is quite loud, so I will do that side. Okay, hi, okay. I'll mute the YouTube stream and get started. Okay, hi. I'm Yiren and I'll be taking the group actions section. So we'll start with not group actions actually. We'll start with some isometries. So what is an isometry? It is the set of all distance preserving maps in Rn. So it, which means it satisfies this condition here. What this means is basically if you have a point, say 2 points in Rn, A and B, and you take the image of those under some t, and you get A prime, B prime, the distance between these are the same for any pair you pick. So some examples of isometries will be translations. So if you translate a line segment, then the distance between the points stays the same. You can also have reflections and rotations and many more. So a fun fact is that they take the form, they take this form, so it's multiplication by some orthogonal matrix, and then you add a constant vector onto it. Okay. And now an interesting subgroup here is ON. So this is defined as the set of all isometries that fix the point 0. So if we want this to fix 0, we have t of 0 is equal to q times 0 plus c, and want this to be 0. So what we get here, this is 0, so we just have c is 0, which gives us this general form of maps in ON. And this is isomorphic to the set of orthogonal matrices in GLN. And now we look at the two-dimensional case. So in 2 dimensions, every finite subgroup of O2 is isomorphic to either a group of rotational symmetries of an n-gon, or the group of all symmetries of an n-gon. So this is basically rotations or rotations combined with reflections. In chat is still the slides in last year. There are some similarities, yes. Okay, now we look at another subgroup. This time it's a subgroup of ON. So this is the special orthogonal group SON, which is all orthogonal matrices but with determinant 1. So this is also the intersection between the special linear group and the group of orthogonal matrices. And now in 3 dimensions, it's the group of rotations in R3, and we can actually classify all of these, all of the finite subgroups of SO3 into 3 categories. So they are either rotations along some plane, rotations and reflections along some plane, or a group of rotational symmetries of a Platonic solid. And although there are 5 Platonic solids, there's only 3 rotational symmetry groups, because 2 pairs of them are isomorphic to each other. Okay. Now we'll move on to group actions. So group actions start at G sets. So let's say we have some group G. A G set is a set S combined with a map from G times S to S, which this map basically describes how the elements of G act on S. And this map has to satisfy 2 conditions. The first one is basically associativity. So it doesn't matter if you combine the group elements within the group first, and then apply that to the set elements, or if you apply them one by one. And this second one is that the identity of the group fixes everything in S. So once you have a set and a map where these 2 things hold, then you have a G set. So this, you can think of it as a group homomorphism from G to the permutations on S. So it describes how the elements of G kind of shuffle the elements of S around. Now for some examples of G sets. The first one is the group of invertible scalars in R. So this is just everything apart from 0, acting on any vector space over R. So we'll make this example a bit more concrete. Let's say we have some lambda in Rx, and we have some v in, for example, R2. We can define the map as lambda.v is just scalar multiplication by lambda, and it's pretty easy to check that these 2 hold. And this group also doesn't just have to be scalars, you can also have matrices. So if we go all the way up here, back to ON, so this map defines a way how the group of orthogonal matrices can act on Rn. So that is also that also forms a G set. So some more examples. The group of symmetries of a n-gon can act on the set of its edges and vertices, and the set G mod H is a G set under the group action, under this group action, which is a very natural definition of a group action. Okay, now we'll get into kind of like the anatomy of G sets. So we'll start with G stable subsets. A subset of S is G stable if it is basically closed under it's closed under action from G. So writing this out more like writing this out, we would have, so G dot T is in T for any G in G and T in T. So this will be, yeah. And now an orbit of some elements in S is the subset G dot S. So this will be the set G dot S for all G in G. So you can think of this as all the elements of S that you can get to by having some elements of G act on it. And it's also the smallest G stable subset of S that contains S. So some examples of orbits here. Orbits of Rn under On. So I will need some space here. So On is the group of isometries that also fix 0. So what this means is that, so x minus, okay, I'll use v actually. So v minus 0, the distance between v and 0 is the same as the distance between t of v and 0. This is because On fixes 0. And another way of saying this is that the magnitude of v is the same as the magnitude of t of v, which means that On preserves magnitudes. So the orbits of Rn under On would just be the n spheres in Rn. So this is n spheres. And now the second example, the orbits of G mod H when equipped with the standard group action under G. So that was defined up here. So to approach this part, we can just kind of take an element from G mod H and see what the orbit of that is. So we can just take H and let's see what G dot H is. So this is the set G dot H is equal to GH for all G in G. And that is also exactly G mod H. So there's only one orbit here, and that's the whole set. And there is a special name for when this happens. It's transitive action. So G acts transitively on set S if S only has one orbit. So here we can say that G acts transitively on G mod H. Okay, so here's another theorem on orbit structures. So what this theorem says is the G orbits form a partition of a set. So this implies that the G orbits are all disjoint. And the equivalence relation here is that two elements are equivalent if and only if one is in the orbit of another. Okay, now we move on to G-set morphisms. So what a morphism between G-sets is basically a structure preserving map between the two sets. So it's a function phi from S1 to S2 such that this condition holds. What this kind of says is it doesn't matter if you apply phi before or after letting the group elements act on the set elements. So if we have this, then phi is called compatible with the group action or G equivariance. And as usual, if the morphism is bijective, then it turns into an isomorphism. Okay. Okay. Stabilizers. So the stabilizer of an element in S is the subgroup of G of all elements in G that fix S. So an example here, the stabilizers of GH in G mod H. So we want all G in G such that G times some fixed G prime H. Actually, I'll swap these. So I'll denote the group element with G dash. So we want all G dash in G such that the G dash acting on GH, which is G dash GH, is equal to GH. So the only way this can happen is if G prime is actually in H. So the stabilizer here would be H. Now we move on to the orbit stabilizer theorem. So here's the first theorem says that if a group acts transitively on a set S, then we have an isomorphism between G mod, the stabilizer of S, and S. And this is a consequence of the first isomorphism theorem. Now, because we have this isomorphism, we can now also apply Lagrange's theorem to orbits. Now, for any G set S and an element S in S, the set G dot S is it's one single orbit, so G will act transitively on this, which means this is isomorphic to G mod the stabilizer of something in here, and since we have S here, we just take S. And now, so their sizes should be equal, and then applying Lagrange's theorem to this, get to this. So an interpretation of this is that the size of the stabilizer times the size of the orbit is the order of the group. And now we have a longer example. So H and K are two subgroups of some finite group G, and H times K acts on HK according to the map. So you multiply the set element by H1 at the front and K1, the inverse of K1 on the right. So now we want to use the orbit stabilizer theorem. So we want to use this result to show that this equality holds. So I'll write this theorem down here so we can have easier access to it. Equals to G on. Okay, so we want to use this, and what we have to do is figure out how H times K and HK fits into this puzzle. So on the numerator here, we have the group G, which is acting on the set. So a suitable suitable choice for G here will be H times K, which is the group that acts on our set here. So if we calculate the size of H times K, this is just the size of H times the size of K, which is actually our numerator here. So that's a hint that we're going in the right direction. And now, for the other two terms here, they all involve some element S, but so the question now is what element should we pick? And the default choice, and one that we know has to be in HK, is the identity of G, because they are subgroups. So if we let S is equal to 1G, we can look at what the stabilizer of this is. So we want elements of H times K, so let's say HK, that when it acts on the identity, it gives you back the identity. So translating this using this here, we have H 1G, K inverse is 1G. And because this is the identity, we can just kind of remove it. So we have H, K inverse is 1G. So what we have here is H is equal to K. So the stabilizer will be of the form H, where H is in both H and K, because H and K have to be equal. So the size of the stabilizer, of 1. Okay, so it's not G here. Okay. Size of, it should be H times K. This is actually equal to the size of H intersection with K. And that gets us our denominator here. And now all we have to do is show that the orbit of the identity is equal to H times K. So if I scroll even further right here, the orbit will be, so how do I write this out? H times k dot g. This is the orbit of the identity. Is equal to hk 1g for all h in h and k in k. And this is the same as, we can just ignore the right hand side here and just focus on the left hand side part, because it just saves us working out. So this will be hk inverse for all h in h and k in k. So this is just the set of anything in h times the inverse of anything in k, but because k is a subgroup, it's closed under inversion. So k inverse can actually be anything in k. So what we have here is just anything in h times anything in k. So this will be the set hk. And that gets us the left side. So by just plugging all of these results into the formula here, we can get the result we need. And a nicer solution is typed up here. So after the seminar, if you want to have another look, these slides will be posted. Okay. Now, stabilizers of conjugate points. Here are some quick results. So let S be a G set. Then the stabilizer of G dot some point, G dot some element in S is the stabilizer of S conjugated by G. And a corollary of this is, let's say two subgroups of G are conjugate. So H1 and H2 are conjugate, which means this. Then G mod H1 and G mod H2 are isomorphic as G sets. Now we get on to counting orbits. So we start with fixed point set. This is like the last kind of definition in this section. So, the fixed point set of some subset of G is the set of set elements which are fixed by H, which are fixed by everything in this subset. So this is kind of like stabilizers, but stabilizers is the set of group elements which fix a element in the set, and fixed point set is the set of set elements that are fixed by some group elements. And now we get onto this result, which was covered quite a lot in the lectures and also tested on our midsem. So this is the orbit counting theorem, or Burnside's lemma. So if we have a finite group G and a finite set S, then the number of orbits, G orbits in S, is given by the number of orbits is the sum of the fixed point sets of every element in G, the sum of the size of the fixed point sets for every element of G, and you divide that by the order of G. So that's all the theory for this section, and I'll wrap it up with two pretty interesting examples, all from past papers. So I'll do the second one first because this one is more, it's pretty similar to the question we got in the midterm, but there are a few differences. So one is that we do it generally, so for n colors, and now also it's a square, not a, I think, pentagon. Okay, so we want to find the unique colorings of the edges of the square, and two colorings are equivalent if we can get to one from the other by applying something from D4. So what we want to find is D4 orbits of the set of all distinct colorings of the edges of the square. So how we can do this is by using our orbit counting lemma, which is number of orbits is equal to 1 on G times the sum of the size of the fixed point sets over all group elements. So we can start by listing out everything in D4. So what is there? There's the identity. Actually, I'll do it on the side because I will need some more space. We have the identity. We have rotation by 90 degrees, so let's call that rho. We have rotation by 180 degrees, rho 2, and actually I'll do rho squared and rho cubed, or rho inverse for rotation by 90 degrees the other way. So these are the rotations, but we also have 4 reflections. We can reflect along a pair of edges, so we call them sigma x and sigma y. And then we also have reflections along the diagonals, so we call those sigma 1 and sigma 2. And all we have to do now is count the size of the fixed point sets of each of these elements, sum them up, and divide by 1, 2, 3, 4, 5, 6, 7, 8. So we can actually start filling this in right now. Yeah. So we have number of distinct colorings is equal to 1 on 8 times the sum of all of these. So we'll find those and then add them together. So by the identity fixes everything. So you can just have every single combination of colors on the sides. So we have n colors and 4 sides to color, so this will be n to the power of 4. Now for 90 degrees rotations, what this means is that, say we have a side here, this gets rotated to the next side, so it means that these two sides have to be the same and the same color, and this side, when rotated, turns here, so these two sides have to be the same color, and so on. So all 4 sides actually have to be the same color, and you only have n choices of colors. So the two 90-degree rotations will only have n elements in their fixed point sets. And the 180-degree rotations basically just swaps pairs of swaps the opposite edges. So you have two places to color in and n choices, so this would be n to the power of 2. And now rotations along the vertices is pretty similar. So if you rotate along this diagonal, these two edges get swapped and these two edges get swapped. So they have to be the same color, but there's no restriction on what the colors can or can't be between the other faces. So again, you have two places to color and n colors, so this will be n to the power of 2. And now reflections along the edges is the interesting part. So if we reflect along this edge, these two sides get fixed, so they can be anything they want, but these two get swapped, so they have to be the same color. So there's 3 places to color in, so these will be n cubed. And the result you get will be n to the power of 4 plus 2 n to the power of 3 plus 3 n to the power of 2 plus 2n. Okay, and again, the solution is also typed up. Okay, now I'll move on to the last example. So, if I can find it. Okay, here. This is a 2020 past paper question. So, let G be a finite group acting transitively upon a finite set with more than one element, and show that there is an element without fixed points. So, how do we do this? And how do we get the idea on how to do this? Well, this is actually a part 3, and part 1 and 2. Part 1 gets you to state this result, and part 2 gets you to state what transitively means. So that's a clue to use both of these pieces of information in our solution. So what does transitively mean? Transitively means the set only has one orbit. So if we apply that here, it means that we should get 1 is equal to 1 on the size of G times the sum of the sizes of the fixed point sets. And now we want to kind of cook up a contradiction argument here. So what we can do is suppose every fixed point set is greater than or equal to 1. So no elements in G don't have fixed points. And what we get here is the sum of, if we assume this, then the sum of S, sum of the fixed point sets, since every one is larger than 1 and we have G of them, this has to be greater than equal to the size of G. And if we can somehow show that this is strict, then we will have 1. 1 is greater than, 1 is strictly greater than 1, which is a contradiction. So we want to find some elements in G that has more than one element in its fixed point set. And again, we can look at the identity. So the fixed point set of the identity is everything in S. Everything in S. And we know that S has more than one element, so this has to be larger than 1. So if this is larger than 1 and everything else is at least 1, then what this means is that this sum is strictly greater than G. So we have 1 is equal to 1 on sum of G, and oh, I'm turning into a circle. Alright, I'll drop this out, which is equal to 1 over G times this sum, which is strictly larger than size of G on G, which is 1, which is a contradiction, so there has to be some elements in G without fixed points. And again, this solution is typed up. And that wraps up my section. I will pass it on to Martin for some rings. Okay, bye.
Okay, am I streaming? Cool. Okay. Onto rings. I'm Martin. Yeah, let's get into it. So, what is a ring? Well, a ring is a set equipped with an additive and a multiplicative operation. And it's similar to a group. You can almost think of it maybe as an extension of a group. So, under the addition operation, we have to have that where R is an abelian group. So I mean, should remember abelian group stuff from maybe earlier, but okay, R is closed, addition is associative and commutative. We've got the additive identity. We'll just denote this as 0. Okay, and then every element in R has an additive inverse. We usually denote that as just like with a negative sign in front of it, like negative R, if R is the element. Okay. Just a sec. Okay, moving on. For multiplication, we just have to have closure and associativity. Oh, and we need the multiplicative identity. At least in this course we do. Multiplicative identity we just denote as 1. And remember additive was 0. For all rings except the 0 ring, the ring with only one element, or you can call it the trivial ring. For all rings we have that 0 unequals to 1. Again, other than the 0 ring. Note that for multiplication you don't need an inverse, and multiplication doesn't need to be commutative. Okay, in addition to these two things, we need the distributive property of multiplication over addition. So these two things. You don't get one from the other because multiplication is not necessarily associative. Okay, onto ideals. So let's say we have some additive subgroup I of our ring R. We kind of want to mimic the idea of quotient groups. And we ask ourselves, what properties do we need on I so that R on I, which we know is a group, but what properties do we need on I so that this is also a ring? Well, let's look at the cosets. when we consider it as like a quotient group. Okay, it's all of these things. If we want multiplication, I mean, this thing holding is ideal, right? Kind of want to be able to just say that. Yeah, because we're kind of considering, hopefully, I as equivalent to 0 in our quotient ring. Well, then we've got to have this identity. We've got to have that, I mean, just using normal distributing multiplication normally, we get that this equals this. And then we want this to kind of be AB plus I. So that means this has all got to be in I. And so we impose the restriction that these two things have to be in I, because we know that this one is going to be in I. Yeah, so that's what motivates our definition for ideal. We need that for all A in R and for all I in I, that AI is in I. Okay, here's the definition. Let I be a subgroup under addition of R. Then I is an ideal if, well, it's an additive subgroup. And for all R in R and X in I, we have this sort of closure, both by left and right multiplication. Okay. We can also denote this as Ri has to be a subset of I, and IR has to be a subset of R. Alternatively, you can write these two things as just having to be equal, because we know that 1 is in R, so we can always get an element of I just by multiplying by 1. So yeah, we can have these two conditions as well. I'm going to call this maybe the multiplicative condition, or I'll call it closure under external multiplication, and this is just closure under addition. Okay. Yeah, this is the syntax we use for denoting ideal. Note that it's the same as a normal subgroup. The idea being they're pretty similar things. Okie doke. So, oh yeah, note that 1 does not need to be in I. And so I may not be a subring. We didn't introduce subrings, but subrings have to contain the multiplicative identity, the additive identity, and be a ring, and they have to be a subset. But yeah, I might not be a subring, and if I does contain 1, then I is identically R, because R1 equals R, but this is a subset of I by the multiplicative property. In fact, if we have any element U in R, such that there exists a multiplicative inverse, so such that there exists V such that UV equals 1, well, and VU equals 1, well, then we also have that if I contains U, then I is R. Because you can just take any element R, and you know that R U inverse U, we're denoting this V as U inverse. Well, then R inverse U has to also be an element of I. But that means we have this equals R. So every element of R is in I. And we denote the elements that have this property, that have a multiplicative inverse, we call them units. Units, and you can say the set of all units of a ring, which actually forms, does it form? Yeah, I think it forms a subgroup under multiplication. It is, we denote it like this. Or maybe like this. I forget. Okay, question. Let I and j be ideals. Prove that the sum, prove that the sum, which is defined like this, is also an ideal. And then we're asked if this is an ideal. So I'm just going to denote this one as ij. Note that it's you take pairs from I and j and you just like multiply them together to get an element of k. But okay, let's look at the first one, I plus j. Let's prove that it is an ideal. Obviously it's going to be an additive subgroup. We get that result from group theory because remember R is an abelian group under addition. So if I plus j, obviously an additive group. Now I just need to show the multiplicative property. So R, okay. We say let R in R, and we can denote any element of I plus j as just like I plus j. So let I plus j is in big I plus big J. Then we want to show that this is an element of I plus j. But if we expand this, remember we can expand, then this is an element of I and this is an element of j, because I and j are both ideals and so closed under external multiplication. So this is obviously going to be an element of I plus j. We can also just write this as R. I'm going to use some fun notation. Equals R. I should say it's a subset. Subset Ri plus Rj equals I plus j. Yeah. So that's then we show that then we see that I plus j is an ideal. Okay. Let's just look at the proof that's written down here. Yeah, we also have to consider the right ideal. So here we showed that R I plus j is a subset of I plus j, but we also have to show that it's closed under right multiplication. But just the same argument basically for holds for that. Okay, let's think about k. So this is a bit of an open-ended question. We have to decide whether k is an ideal or not. As it turns out, it isn't. But yeah, it's a good idea to ask ourselves, like, what properties does k have and what doesn't it have? So R, I'm going to denote k, by the way, as I product j. So Rij should just equal Rij equals Ij. And similarly for right multiplication. So we have that k satisfies the multiplication property. But does it satisfy the closure under addition? Well, let's see. Let's say we have Ij, an element of k, and let's just say AB also an element of k, where A is in I, B is in J, I is in I, J is in J. We ask ourselves, is this an element of k? Like there's no real easy way to factor Ij plus AB. Like we just don't have enough information here. So that's why we can think that, okay, it's probably false. K is probably not an ideal. But if k is generated by a single element, that is to say, well, no. If I and j are generated by, if either of them is generated by a single element, then you know they will have a factor. That is, if I, if there exists like some x in I, such that we have all elements I are just like Rx or XR. Well, actually, let's say just Rx, and let's say our ring is commutative. Well, then we can always factor the x out of any element in I. And so if both I and j are like that, well, then we can do some sort of factorization, and we'll get that this thing is still in K. So for our counterexample, that means we shouldn't bother looking at commutative rings where every ideal is generated by a single element. Actually, we call these things, so a good candidate for a ring to think about, I mean, let's say we think about all the rings we know, is to consider the ring ZX. This is not a ring where every ideal is principal. Okay, let's see what I wrote later. Okay, we search for a counterexample. Did I write it on the next slide? Okay. No, what space should I use? I'll just make some space for myself here. Okay, yeah, consider ZX. Well, let me just take two ideals that aren't generated by one element. So I'll take 2x and I'll take 5x, say. If we think of, so let's say this is I and this is j. And we think about k. Well, then it's like every element in this form, 2a plus xb times 5c plus xd. A, B, C, D can be any element of R. Okay, so we got this thing. Well, we naturally see that any element we form has these two divisors. So if we can assume that the this additive property holds, and then reach a contradiction, then we've shown that k is not necessarily an ideal. So we have that k is an ideal, implies additive closure, and now we seek to prove that that can't possibly be the case. So let's assume additive closure and find some element of ij. Well, find two elements of ij, sum them, and show, because we're assuming additive closure, we'll sum them and we'll show that if we don't assume additive closure, that element can't possibly be in K. Because I have these two factor things, what I'm going to do is I'm going to look for an element that, such that the only divisors of that element are the unit. Because we notice that plus or minus 1, which are the only units in this ring, we pretty easily notice that this is not an element of I nor j. And the reason is if we expand this representation, we'll get that if it's an integer, it has to be 10 AC. Well, we'll get 10 AC plus some other terms containing x. So if it's an integer, then it's got to have a factor of 10 in it. But plus and minus 1 clearly aren't. Okay, now let's think of an element. Well, I can take an x here and an x here and get an x squared. And then how about I just sum and I just add a constant term to this. So what constant terms can I form? Well, I can get the 2 and times by 5. So know that 10 should be in K as well. So assuming additive closure, we should have x squared plus 10. I've chosen these numbers so that we get an irreducible polynomial. So obviously x squared plus 10 does not factor. well, the only divisors of x squared plus 10 in zx is plus or minus 1 and x squared plus 10, or plus or minus x squared plus 10. Okay? But then if x squared plus 10 is in K, then we should have two things of this form that should equal it. But obviously that can't be the case because we can't form plus or minus 1. So like the only choices for these two things are going to be one of these. We can't have that. Because again, nothing contains plus or minus 1. Like neither I nor J does. So we get a contradiction. So we've shown that K is not an ideal. Okay. And I mean, this is the example that they've used. They've used X. They've saying that clearly X is not in K, but then assuming additive closure, X should be in K. But we just did a different approach. Either is fine. Cool. If R is a commutative ring, so that means that multiplication commutes. Doesn't matter what the order is for multiplication. Let I be this set. Prove that I is an ideal. Suffice to show, and I'll explain later, this is a neat property, we just need to show additive closure and the multiplicative closure, well, external multiplicative closure. So let's start with additive closure. Oh, I should add there's one more thing we need to show, which is that it's not empty. So for additive closure, I'll say, suppose x, y is in I. So we need to show that x plus y is in I. Well, then we have that x to the n equals 0, y to the m equals 0 for some integers x, n and m. Okay? Now, let's consider x plus y to the, I'm going to call this big N. We need to find some big N. Oh, I'll call it something different just so I don't get confused. Call this J. We need to find some J such that x plus y to the J is 0. So let's think about that. What should our J be? Well, if I expand all the terms in x plus y to the J, I would really like to get 0. I would like them that they all cancel out. So let's consider the terms. They're in the form of, I'll just say ith term. I can start from 0 though. Ith term is x to the I, y to the j minus I. And we'd like to use this property, right? So we know that this is 0 when I is greater than or equal to n. That makes sense, right? Because then we can split x to the I into x to the n times x to the I minus n. Yeah. And so, yeah, this is 0 when I is greater than n, and, or I should say, or j minus I is greater than or equal to m. That would be this coefficient, this term is 0. Well, I can combine these two properties just by summing the two inequalities and get that j has to be greater than n plus m. So let's just set j to n plus m. Then we see that x plus y to the n plus m equals 0. Because either the x term or the y term in each of the expansions of this, oh, I forgot the binomial coefficient, but it's something like this. We don't really care about in this case. Every term in that expansion is going to be 0 in this case. So we get additive closure. Also note that I is non-empty just because 0 to the 1 equals 0. So it contains 0. Okay. In this proof, they just go over I plus being an abelian group, but that is technically not necessary, and I'll talk about it later. Like what we proved was enough for the additive part. Okay. Ooh. Anyway, I'll just jump right to part 2 for showing that Ri equals I. We'll take R and X and I, right? We have to show that Rx is an I. And we only know the property that x to the n equals 0. So we want to show that we want to do some manipulation so that we can use this property, right? So because of commutativity, we can just rewrite this as r to the n times x to the n after expanding this. And we know x to the n is 0. So that multiplicative closure is actually a bit easier. So we've shown that Rx equals I and XR is also in I by commutativity of I. So we have that Ri equals IR. And just note that, yeah, one only needs to show closure and addition and this thing, which we've just shown. So why is this the case? Well, you can get the other you can get the other additive abelian group properties. I'll show you why. If you have this multiplicative property, well, then you can just say -1 I is a subset of I. But that means all the inverses should know that -1 times A equals -A for any A in a ring. So this is how we get inverses. For 0, if we have non-emptiness of I, then, well, 0I can take 0I because of this. 0I is a subset of I, so 0 is a subset of I, because 0 times anything is 0. So yeah, it's enough to just show these things and non-emptiness. Okay, suppose I1 up to In are ideals. Then a nice property is that their intersection is an ideal. Okay, their intersection is obviously a subgroup under addition, just from group theory. But let's look at why Ri equals I. Pretty simply, just take I in I. Well, this implies I is an ij for all j. And then we can use the property here that these are all ideals. So, I mean, we definitely want to make use of this property. So let's use it. Each of these we already know to be ideals. So let's just say for all r, I and for all I in I and R is in R. Well, okay, we have I is in I implies I is in ij for all j, which implies Ri is in ij for all j. That's using closure under external multiplication for ij. But this just simply implies Ri is in the intersection, which equals I. Yeah, because we have it for all j. So it must be in the intersection as well. Pretty neat. Next, if R is a field, then there are precisely two ideals. The zero ideal and R. The idea being that any non-zero element in the field, you can take its invertible. And we've shown previously that if an ideal contains a unit, an invertible element, then then the ideal is just the whole ring. Alternatively, you can just times by the inverse to get 1, and then you know you've got R. And there's the zero ring as well, because 0R equals R. And you know that 0 anyway is an abelian group, just a trivial group. Actually, this statement here is an if and only if thing. So R is a field if and only if there are precisely two ideals. It's a good thing to keep in mind. And we'll use that property as well. Okay. Let S be a subset of R. The ideal generated by S, I've already used this notation, but the ideal generated by S is the intersection of all ideals containing S. So it's in some sense the smallest ideal containing S. And if we have S1, S2, etc. in S, well then S is all angle brackets S is just all combinations of this form. R1 S1 T1 plus T1 T2 S2. I'll put R here. Plus R2 S2 T2 plus so on, where you know that S1 S2 etc. is in S and R I T I is just in R. So it almost looks like just linear combinations of this form. In the slides, you'll sometimes see this notation being used for the ideal generated by an element, but we use this angle bracket notation as standard in this, is what's standard in this course, although more standard is this usage. Yeah, you might see this syntax used in these slides. That tends to be more standard syntax, but we'll just use this. If I is finally generated, we can express I using alpha 1 up to alpha n. Okay. We call I a principal ideal if it's generated by one element. We spoke about this before for an earlier problem. Yeah, if we can write I as angle brackets alpha for some alpha, well then it's a principal ideal. Okay. Let's show that this ideal in ZX is not principal. Basically, we're just going to proceed by contradiction, right? You assume, okay, it is, let's just say it is principal. Let's find something wrong with that claim. So I'm going to call this ideal I. I'm going to call this polynomial P. And we can say sup pros I is principal. So that means it's generated by alpha for some alpha in ZX. Okay. Then R alpha equals 3 for some R. And similarly for P. So we can say R divides 3 and R divides P, where P is our polynomial. But R divides 3. What do we know about this? Let's try to restrict what R's we can have if we have these two things to be true, right? The idea is that we keep on restricting it until we get the empty set. So R divides 3 implies, well, R is going to be a polynomial of 0 degree, because if you multiply any element of ZX by a polynomial, it can only increase in degree if it's a polynomial of degree 1 or greater. So R divides 3 implies R is either plus or minus 1 or plus or minus 3. But then what does that say? Okay. If R is plus or minus 3, because we'll take cases now. Okay, if R is plus or minus 3, that implies plus or minus 3 divides a polynomial P. Again, we have this assumption. But that obviously can't be the case. I mean, if you try to divide by 3, you're going to get fractions as a coefficient, but we're in ZX, so we only have integer coefficients. So that's impossible. Okay, alternatively, if r is plus or minus 1, well then our ideal I contains the unit. So that should imply I is r. But is this the case? Or you can just say, like, does I contain 1? Yeah, obviously obviously 1 is not in I, because we need to get our contradiction. And let's think of why that's the case. Obviously 1 is not an I because elements of I are in the form of 3a plus pb. But then if we equate this to be 1, so again a and b are just any random elements in zx. If we equate this to be 1, well, our polynomial term has to be 0, so b must be 0. But then we get that 3 would divide 1. Impossible. Okay, yeah. Obviously 1 is not nice, otherwise we would have this. It would have that 3, it would imply that 3 is invertible, but not in this, because we're just dealing with integers. Yeah, 1 on 3 is not in our thing. Yeah, here's the proof. Yeah, I guess they use that x is not in there. But we just showed directly that plus or minus 1 is not in here. Both approaches are fine, I guess. Maybe it's easy if you show that x is not in there. Because yeah, if you got a polynomial of degree 1 in here, it's gonna have to be like 3x. Okay. Ideals of quotient rings. Here's a fun result. So the quotient homomorphism, which sends an element of R to its coset of the ideal J. This induces the following bijection, which is a bijection between ideals I in R that contain J to just simply ideals in the quotient ring of J. So there's a bijection, which means they correspond to each other, and it's simply via this map. It's simply the image of the ideal I under pi. So ideals containing J correspond to ideals R on J. I'll just add that there in R. So they'll have the same they'll be the same number if there's a finite number, for example. Okay, let I be an ideal of R. We call I maximal if we can't quote unquote fit another ideal between I and R. So I is maximal if there is not another ideal J such that I subset J subset R, and J is not R, and J is not I. So basically, if you have I subset J subset R with I and R ideals, then this should mean that either J equals I or J equals R. Yeah. So I, if it's maximal, it's in some sense, yeah, the biggest such ideal you can have without extending yourself to the whole ring. Okay, theorem. Take an ideal in R, call it I. I is maximal if and only if R on I is a field. This might be a little more difficult to prove directly, showing that multiplication is invertible in R and I, but I'm just going to use our fact from before. Yeah, so how I'll prove this is that, well, ideals of R on I correspond to ideals in R containing I. Yeah, but we have that J contains I, and J is an ideal, implies that either of these two things implies J equals I or J equals R. So only two ideals have I inside of them. So only two ideals contain I, which implies R on I has only two ideals. So it's a field. Again, we used the fact earlier that R is a field if and only if it has two ideals. Okay. This here is a tough problem and probably requires a bit more theory. We'll introduce some more concepts, I guess, before we do this problem. So I'll skip over that and we can quickly finish up with, I think, Chinese remainder theorem. Yeah, Chinese remainder theorem for rings. If R is a ring and you have a bunch of ideals in R, such that if you take any two of them, that their sum is R. Well, any distinct two of them. Yeah. Okay, you can also think of this thing as similar to coprimality. You can think of this as being similar to there exists I in II and J in II such that R, and elements R and S in R such that Ri plus Sj equals 1. So yeah, this is in some sense an extension of coprimality that you would see for like integers. And it's similar to Chinese remainder theorem for groups, how we assumed like coprimality between two integers. Okay, yeah, so suppose this, and let I be the intersection, which we know is also ideal. Chinese remainder theorem gives us the following homomorphism. It says R on I is isomorphic to R on I1 times so on times R on IK via this homomorphism. Yeah, we just send any element of R in the coset. From its coset, we take an element R, we just send it to like this corresponding coset in each ideal. Okay. So, yeah, another way of looking at this fact is to say, it's just that there exists some I and some J such that I plus J equals 1. Earlier I said Ri plus Sj equals 1, but you know that Ri is an I and is an II and Sj is in Ij because they're both closed under external multiplication. Yeah. Okay, then the element 1 belongs to the ideal, so it generates all of I. Yeah, that's a similar way of looking at this property. It's kind of like coprimality. Okay, just a quick question. Let M1 not be equal to M2 and have them both be maximal ideals in R, which is commutative. And suppose I equals their intersection. Okay, prove that R and I is isomorphic to the direct sum of two fields. Well, given that these two are maximal, I want a direct sum of two fields. Well, we know from earlier that M1 being maximal implies R on M1 is a field. So we know R on M1 and R on M2 are fields. We saw this fact earlier. Okay, so direct sum of two fields. I'd really like to take just this, right? So, and we're also hinted at the intersection between them. And we want to prove that that's isomorphic to the direct sum of two fields. So we want to so that's why we could think that maybe we show that it's isomorphic to this, and then you should hopefully get reminded of Chinese remainder theorem. So we want to show this thing, and this is a result of Chinese remainder theorem, but that's only if we can show that m1 plus m2 equals r. And this is going to be the case for any pair of maximal ideals pretty simply, because if you take, let's just say, take I in M2 such that I is not in M1. And we can find such I because we have by hypothesis that these two are different, yeah? So, well then, M2, I'm just going to, hang on, I'll just use this notation. Then M1 I, just say the ideal generated by these. Then this is also an ideal, right? Because M1 is just a subset, and then we can add I to that subset. Is ideal. But we know that M1 is maximal, so the only ideal bigger than it, and we have that this is definitely ideal bigger than M1 because M1 doesn't contain I. Bigger than M1, so it is R. Well, what that will imply is that, well, we know that 1 is an element of R. Yeah. Cool. So we have the property that M1 plus M2 is equal to R. So that allows us to apply Chinese remainder theorem and get this isomorphism. Okay, let's just look at the answer here. Yeah. We have this since they're maximal. Okay. I'll leave it here. Yeah, and we'll continue with rings in the next one, the next seminar. That's it.